All right, now we're moving on to carboxylic acids and esters. So again, we're looking at that carbonyl group and different ways it can bond and the different functional groups it can make. So carboxylic acids, the functional group is the carboxyl group, which is COOH. You'll see that a lot. The COO group is sometimes referred to as. It's an organic acid, so it is an acid, but it's not a very strong acid usually. They're weak acids that are found in citrus fruit, crab apples, etc. So when you taste lemon juice, that's an example of an organic acid or carboxylic acid. Most common is vinegar, that's acetic acid. And, oh, there we go. Okay, so I'm going to show you what this COO group looks like. So let's say you have a 3-carbon chain that's a carboxylic acid. We have that carbonyl group, but we also have an OH. So you actually got carbon bonded to 2 different oxygens. One's a double bond to an oxygen, the other is a bond to a hydroxyl group. So that is your carboxylic acid functional group. All right, naming carboxylic acids. Step 1, you name the parent alkane. Has to contain that COOH, or that carboxyl group. Replace the E of the alkane with oic acid, and the carbon atom of the carboxyl group is always given position number 1. Name and number the branches that are attached to the compound. So here are some examples. I don't know if I can just delete those boxes. So let's see, we got 2 carbons here with your COO group, and if you end up circling it like I'm doing, that's totally fine. So there's your carboxyl group with 2 carbons attached to it. So the parent alkane is ethane, but your rule for carboxylic acid is we drop the E and we add oic acid. Oops, acid. So this ends up being ethanoic acid. There we go. Next one has only 1 carbon in it, so that ends up being methanoic acid. This is a 4-carbon chain. Ends up being butanoic acid. Notice how I didn't need to put 1 butanoic acid because that carboxyl group is always on the end of the chain. Properties of carboxylic acids. They're polar compounds due to that OH and the carbonyl bonds. Because it's got that polar hydroxyl group, you can have hydrogen bonding. So that means we have higher melting points and boiling points. The first 4 simple carboxylic acids, so that's meth, eth, prop, and bute. Methanoic, ethanoic, propanoic, and butanoic acid. They're miscible with water because of those polar parts of the molecule. Solubility, however, decreases as the number of carbon atoms increases because you end up with a very long hydrocarbon chain that's nonpolar. So as you get longer and longer chains, you actually end up becoming more and more nonpolar, even though the end still has that polarity. Because of the strong hydrogen bonds between molecules, the melting point and boiling points of carboxylic acids are very high. Okay? Notice how now, here's sort of a chart with different boiling points. Again, your alkanes have the lowest boiling point. So notice how as we go up here, we're increasing. Then your aldehydes and your ketones are pretty close together because of that carbonyl group. Alcohols jump up even higher because they can make hydrogen bonds. And now your carboxylic acids can make hydrogen bonds and they have that polar carbonyl group. So they're the highest melting point and boiling point of all the compounds we've seen so far. All right, if we look at the acidic properties of carboxylic acids, this is important. The hydroxy group in a carboxylic acid does not behave like a basic hydroxide ion, OH. Oxygen has a high electronegativity, and there are 2 oxygen atoms present to help carry the extra negative charge that is caused when a positive hydrogen atom dissociates. So what we end up having is sort of like a resonance structure. So here is my carboxylic acid. What will happen when it actually acts as an acid is that it's actually going to lose that hydrogen. So remember, your definition of an acid from grade 11 is something that will donate a proton. A proton donor is an acid. So there's a proton or an H that can be donated from these acids, okay? So if you just quickly look down here, this is incorrect. You're never going to get carbon with a positive charge and it breaking off to make a hydroxide and trying to make something that's basic. This is never going to happen because this positive carbon, it's basically called a carbocation, is quite unstable and will not readily happen. So this does not happen. Okay. at the top in blue, this does happen. So when we lose this hydrogen, there it is right there, now we have an extra negative charge left over on this oxygen. Here's the cool thing. We can actually form a resonance structure. I'll show you what the resonance actually looks like. What will happen is this extra negative charge can actually bounce in here and make a double bond and kick out one of the double bonds there. So you can end up with a double bond on that oxygen and then a single bond and a negative charge on the top oxygen. Okay? So that's what I mean by the two oxygen atoms can sort of carry that negative charge. It ends up being a lot more stable than the bottom option. So that's why they can act like acids. All right, how do we make carboxylic acids? We know that a primary alcohol can get oxidized to an aldehyde. The aldehyde in turn, so when that happens, remember, we're going to take off these two hydrogens, and they're going to bond to my oxygen to make H2O. What am I left with? I'm left with this bond on my hydrogen coming and making a double bond with oxygen. So that's how I got that, and I still have the hydrogen on the bottom. So there's my aldehyde. Now, step 2, if we further oxidize it, so if we take that compound and add more oxidizing agent to it, what can happen? Oops, sorry. In this case, we're not going to remove hydrogens, but remember your definition of an oxidation reaction. It's to increase the number of bonds to oxygen or decrease the number of bonds to hydrogen. So what's actually going to happen? This carbon is going to increase its number of bonds to oxygen and decrease its number of bonds to hydrogen. It's actually going to undergo both. You don't really need to know how it happens. All you need to know is basically this oxygen gets inserted into there. The oxygen ends up bonding to the carbon, and then it holds on to the H that's there. All right, the breathalyzer test. You guys heard of that, I'm sure. It's actually an oxidation reaction that tests for alcohol in your breath. The oxidizing agent is actually the chromate ion, which changes from +6 to +3 in the reaction process. Now +6 is an orange color and the +3 ends up being a green color. So if you have alcohol that could actually become oxidized, then what will happen is the solution will change from orange to green. So that's basically what happens here. So again, we've got an oxidizing agent. We're going to remove 2 of the H's to get your aldehyde. Okay. And then again, if it gets oxidized again, you're going to add in that oxygen here so that it ends up making an OH group there to make your carboxyl group. And if that's the case, then your chromium ion ends up being green. All right, esters. What are esters? Think of esters as cuckoo crazy. Like I have a friend whose name is Esther and she's cuckoo crazy. So a lot of people get confused between esters and ethers. Just remember esters is cuckoo crazy and ethers are just not. So the functional group is called the alkylated carboxyl group, or COO-R, okay? If I put a C here and I read it this way, coo, crazy, that's how I remember the ester group. Low molar mass esters have a very pleasant fragrance, so they're used in perfume, soaps, and such. And they're made from the reaction of an alcohol and a carboxylic acid together. When we name esters, you have 2 basically halves of the chain, kind of like in an ether. However, it's a little bit different because we have the extracarbonyl group. So you have to identify the main part of the ester, and your definition of the main part of the ester is the part that contains the carbonyl group. This comes from the parent acid. Begin by naming the parent acid. Then you replace the oic acid with OH. And then you name the second part of the ester as an alkyl group that's attached to the oxygen atom. Name this as you would any other alkyl group. So then we put the 2 names together. Note that esters are named as 2 words. So let's check this out. This is called butyl ethanoate. So the ethanoate, that's your main part of the ester. That's the part that contains the carbonyl group. So in this case, it was ethane or ethanoic acid. We changed the ending to OH, okay? And then you name the other part that's attached to the oxygen. In this case, it's 4 carbons on, so that's how we got butyl. Okay. If we actually were to make that compound, which we can in class, we can actually make a banana smell. So that's actually going to be part of our lab that we're going to do next week. If we flip it and put a 4-carbon chain up with the carbonyl group, the ending ends up being butanoate. And here I'll color code this. Now I have 2 carbons here. That's your ethyl group. So this one is ethyl butanoate. That one ends up spelling like pineapple. Other esters that we probably won't be able to make in the lab are pentyl acetate, octyl acetate, so it's got 8 carbons, and pentyl butyrate. Okay, that's apricots. So just some other examples. Lipids are also esters. So those of you who've taken biology, here is the tristerin molecule, which is, or triglyceride, which is how we store fats, okay? These are esters, okay? It's actually a polyester. Ooh, I'm sure you recognize that word. Anyways, so here are 3 ester groups in your lipid, okay? You don't really need to know these molecules. It was just a quick connection that I wanted to make for those who were taking the biology, okay? So now you know some other examples of esters. All right, properties of esters. They're polar molecules because, again, they have that carbonyl group, but they don't have the OH group on them anymore because it's bonded to another chain, so it actually cannot make any hydrogen bonds with other molecules. It's slightly soluble in water, again, because of that polar carbonyl group. But if we increase the chain too much, it ends up becoming more and more nonpolar. They have not very low, but lower boiling points due to the absence of hydrogen bonds. And okay, preparing esters, the esterification reaction. So this is actually kind of a simple reaction once you sort of get the hang of it. The name of it is simple. You're making an ester, esterification. So here's what happens. It's an example of a dehydration synthesis reaction because water is produced and you synthesize an ester. So there's your dehydration and your synthesis. So we're going to react a carboxylic acid and an alcohol together. Conditions: you need concentrated sulfuric acid and heat. All right, so here is an example. So what I want you to do is watch how this works. Here is your carboxylic acid. I often just call them CAs, okay? You've got your COO group there. Here is an alcohol. I'm going to rewrite this a little bit. I'm going to put, say, 2 carbons on it, okay? But I'm going to put the OH group here and then throw 2 carbons on it, just to make it a little bit more simple. So now I'm just going to erase my COO group, or my carboxyl group. So here's what happens. At dehydration, I've got to remove water. So you're actually going to remove that hydrogen and this hydrogen and oxygen. That's your water molecule. And you end up writing it over here in your products. Okay. What are you left with? Well, you're left with your carbonyl group attached to that carbon. Okay, without the water in between. So that's how you get your carbon double bonded to an oxygen. And then there's your another oxygen bonded to, in this case, it would have been 2 carbons. Okay? Coo crazy. There's your ester. Here's another example. Again, I kind of gave you the one with 2 carbons on it already, but at least you can sort of see, okay, there's your water molecule coming off, and you end up with your cuckoo crazy bond, your ester bond, and water. All right, reactions of esters, hydrolysis. This is the opposite of your esterification reaction. Your ester bond ends up being split into 2 to form 2 different products. Produces the salt of a carboxylic acid and an alcohol, and it's carried out in basic solution and usually requires heat. So the esterification reaction needed an acidic solution. The reverse needs a basic solution. It's also called saponification. This is how soap is made. All right. So what happens here? Here is your ester, cuckoo crazy. Okay. When you add a base, what happens is you're actually going to break the bond there. Okay. So this is where it's going to break. So the sodium hydroxide is going to come in and break it. You're going to end up with a negative charge on your oxygen, okay? That's going to attract the positive charge on your sodium, okay? So that's how I got this product here, okay? That is the, where does it say in the notes here? Sorry, produces the salt of a carboxylic acid. That's what that is. Okay. What's left over? You've got your 2 carbons here that were cleaved off, and you've got an OH group. That's going to go on that carbon, and that's how I ended up with this alcohol. All right, so if we fill in our flow chart, what did we add in today? We added in carboxylic acids, esters, and we actually added in another alcohol over here. The reason I added it over here is just because I didn't want to have an arrow that kind of went like that up to alcohols, but it basically is the same thing. Okay, so just to keep the chart a little bit more organized, I threw alcohols up there again. So we just looked at on the last slide how to make an ester into an alcohol and basically a carboxylic acid. It does kind of make both, even though it makes the salt of a carboxylic acid, but sort of we focus in on the alcohols. Come on, erase. There we go. Okay, we also looked at, to start, how aldehydes get oxidized to a carboxylic acid, and how a carboxylic and an acid and an alcohol can make an ester. All right, so we're almost done our flow chart. After the next note, you should have this completely filled in. And then I can start to ask you questions such as, make me a carboxylic acid from an alkyl halide. And you have to know to first, if you're starting at alkyl halide, you have to first do elimination. Then you have to do hydration. Then you have to oxidize it twice to get there. Okay, so that's sort of where we're going with this. All right, if you have any questions, we'll take them up in class.